I'm happy to introduce Suji Hong from University of Nebraska-Lincoln, who's going to tell us about C-vectors and non-self-crossing curves for acyclic quivers of finite type.
Hi, thanks for the introduction. I just realized that today is not 24th. I've been getting dates all mixed up this semester, but oh well, COVID. So I'm going to talk about the C-vectors and non-self-crossing curves. So before I start, this is going to be very closely related to Kayla's talk, actually, because I am going to talk about how quivers shows up in a bunch of places. So for example, we can use quivers to define cluster algebras, or use quivers to define path algebras over the quivers. And we can also look at this frame quivers. And with this path algebras, the representation of this path and this quiver, the quiver representations are related to like root system and their dot positive roots, which I will mention briefly later. So what is a quiver? A quiver is a finite oriented graph without any oriented two cycles or loops. So nothing that looks like this or that. So here is an example. But you can see that even though there are no two cycles, there is this cycle of length 3. That's fine. And if a quiver has no oriented cycle, then it's said to be acyclic. So I am going to, and then given any quivers, we have, Bowman and Zolovinsky have defined a quiver mutation that relates to it, which actually is related to Seibert's duality. So in all I'm saying is that given a quiver and a vertex, we can mutate at any of the vertices in this case. So if we were to mutate at vertex I, we get a new quiver. So there is a way to go from one quiver to the other using this mutation. And so we're going to be focusing on acyclic quiver in this talk. And specifically acyclic quivers of type A, D, and E. As Kayla mentioned, A was the one that looked like a path. So any quiver whose underlying graph looks like a path, and D looked like a path, but with one branch down there. And with E, we're going to look at type E 6, 7, or 8. So looking at the ones with number 6 vertices, 7 vertices, or 8 vertices, but these generally look like, where did it go? I don't know what happened to my blue pen here, but green. It looks like something like that, where we have this branch in the third vertex from the right. And with these vertices, with these different fields that are related to quivers, we can look at different objects in them. For example, we can consider like D vectors. We can look at positive C vectors, or we can also look at real shear roots, which are going to be dimension vector of certain types of like the modules of this path algebras. But let's actually define what the C vectors are. So to define C vectors, I first need to define what frame quiver is. So I'm just going to actually show you an example to define what this frame quiver is. So given this Q, we're first going to copy the vertex set, but we're going to actually make them a frozen vertices. So we're not going to mutate on those new vertices. And then we're going to put an arrow between like mutable vertex 1 to frozen vertex 1, so on and so forth. So this is called frame quiver. And because with quiver, what do? We just mutate. So we're going to mutate these in any sequence we want. Let's say that we want to mutate it at 3, and then 2, and then 1. And that's what we end up getting. So in here, the C vector is looks at this new quiver and the relation between this mutable vertex and the frozen vertices. So in here, you can see that there is an arrow from all the frozen vertices to this mutable vertex 1. There is a arrow from vertex 2 to 1 prime. There is an arrow from 3 to 2 prime. So we're going to record this in like a vector form. So this is the vector that corresponds to the mutable vertex 1. So you can see that there are one arrow from each of the frozen vertices to 1. And in both cases, there is an arrow from two, like a frozen mutable vertex to 1 frozen vertex. And what we can notice here is that all of these entries are all non-negative or non-positive. In other words, when we look at a mutable vertex, all the arrows from the frozen vertices are either coming in or going out. So you might wonder, is this a coincidence that it happened only on this quiver? But the answer is actually no. Dirksen, Wayman, and Zolvinsky in 2010 proved that any C vectors are either going to be non-negative or non-positive. So we're going to call the non-negative C vectors to be positive C vectors and the non-positive ones to be negative C vectors. And we're going to be focusing only on this positive C vectors. Okay, so let's go back to this overview. So I just defined the C vectors. Real shear roots, let me just quickly say that that's just going to be like dimension vector of rigid indecomposable modules. But the only thing we actually care about is the fact that these two are equal. And this was proved by Chebs in 2015. And also, when we look at non-initial D vectors of a cluster algebras, like non-initial meaning, like as Kayla mentioned, there's initial seeds. So we're looking at cluster variables that are not going to be initial seeds, and looking at the something called D vectors related to those cluster variables. And then what we know is that these are also equal, which was proven by Caldwell and Keller in 2006. So these objects are very interesting because we just need to prove it for one of them and it's true for the other. It's like they're equal as a set. So we wanted to know more about these vectors. So let's actually take a look at an example of some of these vectors. So for example, if we have this quiver, 1 to 2 to 3 like this, these are some of the possible C vectors. We get 1, 1, 0, 2, 2, 1, so on and so forth. And I don't really notice any patterns in them. So we wanted to see if there's a simple way to describe these objects other than going through all the process. So before I move on in here, so like I mentioned, these are related to the root system as well. So from here on, instead of writing them as vector, I'm going to write them as a root. So it'll be alpha 1 plus alpha 2. This will be 2 alpha 1 plus 2 alpha 2 plus alpha 3, so on and so forth. So basically, the first entry is represented by alpha 1, second entry is represented by alpha 2, and the third entry is represented by alpha 3. So we're going to use the root notation for these. So to give a diagrammatic description for this, Kyung-Young Lee and Gyuan Lee, Kyung-Young is my advisor, and he claims that this diagrammatic description is the simplest description you can have. So he wanted to find some kind of diagrammatic description for this. So he introduced this admissible curves on this certain object, which was harder to think about. But thankfully, Felixson and Tumartin came up with this different definition that was easier to understand. So I'm going to use that definition. So in this case, we're going to have this half space, and we have this base point B, and we have this set of marked points, so n marked points if there are n vertices. And then we're going to have these rays. And an admissible curve on this space is given by the smooth continuous function from one of the marked points to the base points, so that it does not cross any other marked points. So it doesn't cross any of them. And then if it's going to cross any of the rays, it's going to intersect transversely. So this is the definition of an admissible curve that Felixson and Tumerkin came up with. We need a way to associate these curves with a root. So here's how we're going to do it. So given a permutation, we're going to label each of the marked points with the numbers in the permutation, basically. And then we see where this curve starts. So that's where this alpha 6 is coming from. And then if you recall, all the rays are passing on the top. And when we follow this curve, the next thing it passes is this ray above 5. So that's why we have this reflection as 5. And then it passes this 4. So we have this reflection as 4, and so on and so forth. So you can see that next thing it passes through is 3, and then 2, and then 1. So that's how we get this representation, how we can associate this curve with a root. So if you're wondering what is this reflection I'm talking about, well, reflection is basically a way to, you can think of this like roots as to be roots on like space, and you're reflecting over some hyperplane. But in this case, I'm just going to think about it this way. So let's say we're looking at this type of quiver. And I wanted to know what the reflection of alpha 6 is over 5. Well, in here, alpha 5 and 5 and 6 are joined by an arrow. So I'm going to say that this is alpha 5 plus alpha 6. And when I take the reflection over 4, well, we can split this over summation to get that. Well, since 5 and 4 are joined by an arrow, we can say that's going to be alpha 4 plus alpha 5. Well, but 4 and 6 are not adjacent. So we're just going to do nothing to 6 and leave it as that. So we can continue this process to figure out what this reflection is, and then what the new vertex is going to be. And in here, one thing I'll mention is that Si of alpha I would end up being negative alpha I. Okay, so Gyeongyung and Gyuan Lee came up with this conjecture that when we look at this set of this non-self-crossing curves, and then look at the associated roots, then that set is going to coincide with the real set of real shear roots. So in here, instead of looking at checking whether it's going to be a C vector of something, or whether it's going to be the dimension vector of some module we want to look at, we can just draw the corresponding curve and then see if it's intersecting itself or not. So this was actually proved for 2 complete quivers. So like in a case, 2 complete quiver is like set of quivers, so that there's at least 2 edges, 2 arrows between all pairs of vertices. And it was proven for Acyclic quiver case very, very recently by Gyeongyung's other student, Sun Yun. So let me just look at how much time do I have left? Okay,
so 2 minutes-ish.
Yeah, let me just quickly go over this. So here are some more examples. So like, let's say that in this case, we're looking at the quiver 1 to 2, the other direction, 2 to 3. And when we look at all these 3 curves, they look very different. Like when we look at this representation, it looks very different, but at the end, they all end up being alpha 1 plus alpha 2. So given one quiver, given one root, there can be many curves that associate to that root. So we wanted to see if there's a way to categorize them. So in a way, we only wanted to find the ones with the shortest length in a way. And then we actually categorize them into something different. We say that this is strictly increasing. We're going to say something like this is non-decreasing. This is going to be positive. And what Gyeongyong conjectured is that Gyeongyong conjectured that non-decreasing, non-self-crossing curves would be enough to describe all real shear roots. And that was his conjecture. And then I looked at this for the finite types, and for type A and D, it is true that the non-self-crossing, non-decreasing curves were enough to describe all real shear roots. But for type E and 6, we had to actually take a union of all this pi, where PQ is the set of arrow, set of permutation, so that the arrow doesn't go the other direction, basically. And actually, for type A, we were able to find strictly increasing curves for all real shear roots of type A. I won't go into how I found that, but I will end here. Thank you.
Great, awesome. Let's thank Suji Hong for a fantastic talk. And does anyone have any questions for our speaker?
I'm not sure if this is something that can be answered briefly, but what special aspects of the finite type case did you take advantage of for this work?
So the fact that real shear roots of finite case is equal to the positive roots.
Right, okay.
So normally the real shear roots is a subset of positive roots, but in this case it's the same.
Okay, yeah.
Is there any connection between these non-self-crossing curves and like the surface model for cluster algebras in these types?
Not that I know of. It seems to be very different than the surface types, like the arcs they were looking in the surface.
All right, let's thank Suji Hong again.